So let's implement what we have learned in a problem. A researcher wants to study the average miles run by marathon runners. So he developed these hypotheses. So he has in mind that, and this is what he put in his alternative hypothesis, H1, that mu is different than 25 miles. Now, let's not ask how did we come out with that, why he's asking this question. Let's take it for granted that this question is a legitimate question and we want to help him out. All right. So when he developed the alternative hypothesis, then the null hypothesis is almost automatic, right? Mu is mu, and then we have the equal sign, and the value for mu naught is the same. So to collect the evidence, he collected the sample randomly of 36 marathons. So this is our sample size n. And he knows that the standard deviation of the population, so for all runners in past data, for example, he had it to be 10. So this is our sigma, right? And found that their mean, so the mean of the sample, is 22.8, right? So this is X bar that he wants to use as an evidence to test his hypothesis. Now, we want to use the rejection region approach first, and later we use the other approach for a significance level of 5%, right? So which is what this is alpha. So what kind of test is this? This is a two-tailed test, right? Because H1 says mu is different than 25. So it's a two-tailed test. Now, how can we find the rejection region cutoff points or the critical points? We look for Z alpha over 2, right? Remember that we said in a two-tailed test, we split the significance level into 2. So alpha over 2 is 5% over 2, 2.5%. So that's Z 0.025. How we get that? We get that from the Z table by looking for the area on the left-hand side of that Z to be 0.975, right? And we get 1.96, which means the other cutoff point on the lower tail is the opposite. It's symmetrical, right? So it's minus 1.96. So we can show it here in this diagram. So I know that these are my rejection region here. It's this one. So we have a right tail here and we have the lower tail here. So if we find values that are in any one of these two red areas, then we reject our null hypothesis. Okay, so these values we got them from the table, minus 1.96 and 1.96. So that's it. We just now want to find our test statistic, which we get it from X bar, right? So Z equal X bar minus mu over standard deviation of the sampling distribution, which is sigma of the square root of n. So we plug all the values in place and we get minus 1.32. So minus 1.32, we look at it, it's somewhere here, right? Because it's greater than minus 1.96. So we can see easily that it's not inside the rejection region, right? This is the rejection region. All right, here we go. So it's not inside, so which means that we're not going to reject HO. Okay, and when we say that, that means we have, okay, when we do not reject HO, sorry, that means we did not have enough evidence supporting the alternative one. That's why we are not rejecting HO. Okay, in the next slide, we're going to use the p-value approach. Okay, so we are asked here to use the p-value approach to test our hypothesis. Also, we are looking for a significance level of 5%. By the way, to find the p-value itself, you don't need to know about the significance level. However, if you want to use the result of your p-value, then you need to compare it to an alpha, and then we need to know what significance level we are looking for. And why I'm saying that? Because we know by definition the p-value is the probability to observe a value as extreme at the value that we got. So we don't really need an alpha for that. Okay, so what we have found is our test statistic that comes from the sample mean, okay, to be minus 1.32. So the question is, because this is negative, how probable it is that we'll see something like that? In other words, what the probability that z is less than minus 1.32? This will be our p-value, right? It's the probability that z less or equal than that plus probability that z greater than the opposite. So that's why we do 2 times p of z less than minus 1.32. And here we go. We multiply that by 2, we get 18.68%, which is very high, right? Which is very likely. And of course, we compare it, if you want, to alpha, which is greater than alpha. So we do not reject HO. So, and even without looking at alpha, look at this. This is 18.68%, right? So we said that it is very likely that when you draw a sample from this population that assumingly has a mean of the mean is 25, it's very probable to find a z value equal to minus 1.32, right? Probable enough to give that evidence for the alternative hypothesis. Okay, and sorry, we did not collect enough evidence about because that likelihood, it's assuming that mu or HO is true, right? So it is very probable, so we do not reject HO in favor of H1, which means we did not have evidence to support our alternative hypothesis.